yeah, let me give you very briefly the outline. I got 3 parts. I will talk a little bit about why we do this, simulating quantum computers. I will bore then the majority of the audience by doing a very quick stabilizer formalism recap, but maybe there are some people here for whom that is new. And then I'll talk a little bit about symmetries in quantum mechanics like you do in your undergraduate class. And in fact, this project was half inspired by having to teach quantum mechanics 1, and then I give you some results. So, I mean, you're very lucky because it's a very recent paper, published November 2024. It's the first time I'm presenting it. And in fact, there's a new a member of the group, Tan Mai Signal, who joined some time ago, who pushed it over the line. He's here if you have technical questions. But actually it goes back a little bit because actually it was a master thesis in 2021 by Valentin Obst and Arne Heimendahl. Very German names, I realize. But actually it was an appendix in a 2018 paper by Markus Heinrich, my student at the time. And so over this long period of time with my mind aging, you start forgetting stuff. And so I was like submitting this abstract to Wiebke, and then I was yesterday doing my slides, and I thought, first time I'm doing this, and then I need an illustration, and so I needed an illustration for Wigner Theorem. So I put Wigner Theorem into Google image search. And then I find this hit, this is a true story, I find this hit, and it's by Arne Heimendahl. It's my former student. I'm like, wow, he gave a presentation on that, which I found on Google image search while trying to find the illustrations. And I was like, Arne, I mean, he could have told me about him giving a presentation. And so I clicked on it because it's a frame from a YouTube video. And not only... not only did he tell me about it, it was also organized by you guys. And I could listen to myself sitting there explaining the stuff to me. Yeah, that's right, that's right. So you young people laughing, this will happen to you too. All right.
You see, it's many words.
Is it? Yeah, okay. So I hope your memory is as bad as mine, so then, you will not be totally bored in this talk. Okay, good. Right, so why are we doing what we're doing? So the motivation is simulating quantum mechanics on, for example, quantum computers on a classical machine. Yeah, we are the anti-Maris. No, she wants to certify that stuff works. I want to show it's not necessary. And so the basic starting point is the question, which subset of quantum mechanics is efficiently simulable? And there's many answers where, I have lots of pictures here that I all stole from Michael's thesis. Thank you. All right. Okay. For example, in continuous variables, we know that Gaussian states and operations, they are classically simulable. No, you can track them in a classical phase space description. And there's this discrete versions, which are the stabilizer states, which I have to rush you through now in the next 3 slides for the 1 or 2 people in the audience who don't know them by heart. Exactly. So quick. What's that stabilizer thing again? Slide 1 of only 3. All right. So stabilizer states, these are the joint eigenvectors of commuting Pauli operators. What's a Pauli operator? Well, you take a Pauli matrix like a Z and an X, and now you have n systems, and you just tensor them together, and then you got these exponents here, which tell you, on which system, what's the power of the Z operator and what is the power of the X operator. And you can do this, for binary numbers here if you have qubits, but you can also do it for qubits, and then you get a related theory. Okay, so can we talk about this a bit more? The operators we get a bit more systematically. Yes, we can. For example, they form a group up to maybe some phases. So if you multiply 2 of these operators together, here also I think this T notation is also Michael's notation. No, I copied it from your thesis, I think. So if you multiply 2 of them together, then these indices, they add up. Okay, so the composition is a sum of arguments, so we have some kind of projective representation of an additive group. And you can also compute, I don't know whether you can see it, you can compute commutators. So if you try to see what happens if you multiply them in different ways, well, you have to move, for example, the X operators of the left Pauli operator past the Z's of the right one. And then every time you get a non-zero exponent, you collect a sign, and you have to keep track of the signs, and it turns out that the phase you get is given by some kind of symplectic inner product. So the word symplectic will appear a number of times in my presentation now. Yeah, but it's not because I like symplectic geometry, it's because the problem demands it. Okay? So in particular, they commute if these phases vanish, and so they commute if and only if the symplectic inner product vanishes. Okay? So what we have is, all right, okay, so now we can say we want to describe joint eigenvectors, so we want to have maximal groups of polys, all of which commute, and now we can translate this into this more geometric language. And that's what I do in this slide. So it's a basis of stabilizer states that corresponds to a maximally commuting subgroup of polys, commuting so that they have a joint basis. And with this translation table I just sketched from operators to their indices, this turns out to be what is sometimes called a maximal isotropic subspace of ZD to the 2n. So let me very briefly explain what's going on here. So D, that is the dimension of an individual system, often 2 for qubits. 2n, n is a number of qubits, but you got it twice because you got the z and the x part. And a subspace means they are closed under addition, so closed under multiplication, so it's a subgroup. And isotropic means they all commute because the symplectic inner product vanishes, and maximal because we want to have unique eigenvectors. Okay, and so now I can now say why, a quantum computer restricting to these states alone is classically simulable, because as the quantum computation progresses, you don't have to write out the expansion coefficients of a state vector in memory. You just have to track efficiently. You have to track how these subspaces evolve, and these are just the combinatorial or geometric data, so that's efficiently doable. Okay. Oh, it's good to go a bit further. That would also be important. So, let's give you an example. And the example is a single qubit. Oh yeah, the picture was here all the time. I haven't explained it. So if you have a single qubit, then of course state space is the Bloch sphere. On a single qubit, you got 3 maximal abelian subgroups of poly operators, namely poly X and identity, poly Z and identity, and poly Y and identity. Right? Each of them have an eigenbasis. So there are 6 states, 3 times 2, and these are the vertices of this octahedron here inscribed into the Bloch sphere. Okay? And so a quantum computation sticking to these states alone and their n-qubit generalization is sufficiently simulable, but it's even more so if you have a state that's inside the polytope generated by them, inside the convex hull, then you immediately get a Monte Carlo algorithm by just taking a state from the interior, convexly decomposing it in terms of the extreme points, flipping a coin according to the relative weight, and then continue your calculation with one of the extreme points. Okay? Okay, so this is ample reason to be interested in this polytope. And so what my talk is going to be about is, understanding this polytope a bit more, of course, not this octahedron, which is, the ancient Greeks had some opinions about, but the high dimensional generalizations. Good. That's stabilizer thing 2 or 3. One more slide, and then I can ask for questions, and then we go into the presentation proper. Okay, so these generalized poly operators, they have a symmetry group. And it's called, confusingly in quantum information, the Clifford group, but too many things are named after Clifford, so the word Clifford group is used in different meanings by other people, so if you search for it online, be careful. And the quantum information Clifford group is a set of unitaries that map polys to polys under conjugation, right? So T of A is this poly operator. If I conjugate, now it's a different poly operator. There's a proportionality sign here because I don't want to worry about phases here. So when does this exist? And so what is the, which kind of permutations can I realize by conjugating with a unitary? And the answer is, this pi map on indices has to be linear because it has to commute with composition. But it also has to be symplectic because it has to preserve commutation relations, because that's what actions by conjugation do. So if you combine that, if it's symplectic and linear, then it's an element of the discrete symplectic group over this discrete phase space. All right, so that's the way I'd like to think about it. Okay, and if you don't like to think about it this way, but more in terms of like gate sets, then it turns out the Clifford group, so these symplectic operations, is exactly what you can generate by Hadamard, CNOT, and phase gates. So any quantum computation composed of these is efficiently simulable, a fact sometimes known as the Gottesman-Nil theorem. Okay, so that ends my very quick introduction. Where can we apply this? And there were two applications that triggered this project. Application number one was a computation of the so-called robustness of magic. Yeah, and so what is that about? So I just told you that if you have a state that is inside this polytope, you can simulate it efficiently. What if I have a state that's a little bit outside? Is there some kind of robust version? And there is. Yeah, there in the past, 5-6 years, there's been a lot of literature on this. It's kind of a quantum information problem of quantum Monte Carlo, of making the sign problem quantitative in quantum mechanics. Yeah, and so effectively, if you have a state that's a little bit outside the polytope, then the difficulty of simulating it scales with the notion of the distance to the polytope. Right? And so people were very interested in computing the distances of states from that polytope. But this is difficult to compute because in high dimensions, as you will see in a second, there's a lot of stabilizer states, so this polytope becomes very complicated. And so even if you have tensor powers, like a tensor power of a magic state, which is a primitive in magic state, quantum computation, computing this distance is a difficult problem. And so what we did a long time ago with Markus Heinrich, a PhD student in the group at the time, is we formulated a symmetry reduced problem. And this turned out to be much easier. So if you, I don't know whether you can see it here, the final line. These are the number of stabilizer states for n qubits. They are astronomical once you reach a modest number like 9. And so you can't run a linear program over a polytope defined by that many vertices. That's impossible. But our symmetry reduction made it feasible. And so we could compute these robustness measures for the first time. But now then the question is, well, what are the symmetries of the stabilizer polytope? So we used a few we could think of, but maybe there's more. Yeah, and so that's what triggered our little appendix, which kind of sketched a way for classifying them back in 2008. Right, and yeah, what I just said, I mean, from my Hilbert space discussion, the symplectic group is certainly among the symmetries, but there could be many more. Okay, so application 2 is the hidden variable model from the dual of the stabilizer polytope, which was of course developed in Vancouver at the time. And so, so if you have a convex polytope and you want to work with it, you know, your central nervous system without your brain even engaging should immediately compute the dual and see what can you do with the dual, right? And this would here be the polar dual of the stabilizer polytope, which is a set of operators that has that evaluate to a non-negative number when paired with the stabilizer state, right? It's a relaxation of the usual physical positivity condition because usually you demand a positivity of, for example, like a density matrix with respect to every psi here, okay? Okay, so what do we know about the polar dual? Well, there's some general theory of convexity, like Farkas lemma or whatever that you learn, in your usual courses, and they would tell you that this polytope, which is called the lambda polytope. So the dual of a polytope is a polytope. In particular, the vertices of lambda are in one corresponds with the facets of the stabilizer polytope and vice versa. It's strictly larger than the quantum state space, no, because we put a relaxation of the usual positivity condition here. It has the same symmetry group as a stabilizer polytope. That's always true for a dual. In particular, then the Clifford group acts on its vertices. And so the figure here is this one that also I stole from Michael's paper, right? So you got the Bloch sphere. Inside the Bloch sphere, you got the stabilizer states. Outside, you get the lambda polytope. And these fancy arrows here, so they are the action of some kind of Clifford, I think, probably action on it. Okay. All right, so the fact that the Clifford group acts on its vertices means you can also make this the basis of a very cool simulation algorithm where you take some state and you decompose this in terms of these extreme vertices here, and then you can also track the time evolution past, through a Clifford gate. And it's very cool because your objects that you use to decompose the physical states are unphysical. Yeah, and so that this still works mathematically I think it's a very nice idea. However, it has the drawback that in order to actually come up, for example, with the initial expansion, you need to understand this polytope better. And so that's the second reason why somebody should, spend more time, or many people should spend more time looking at this polytope. All right, so now that's the summary of my motivation. Namely, we really ought to know as a species more about that stabilizer polytope and its dual lambda. And like the minimal starting point, if somebody gives you a polytope and asks, questions like what's, the combinatorial structure of the phase lattice and all like these fancy things you can ask. Well, the first thing you should know is the symmetry group. No, it's very basic data, and we didn't know at the time. Okay, and that is the summary of my motivation. So if you're unmotivated now, things will only go downhill and pretty fast. Okay, any questions or some?
The converse strongly holds.
Sorry?
The converse strongly holds. If you are motivated now, it will get
very good. Well, let's, okay. Challenge accepted. Okay, so let's stop the talk of quantum information completely and let's go and talk about symmetries in quantum mechanics, and that's going to be like a 10-minute lecture now, like on the quantum mechanics 1 level, and I make the connection later. So here's the thing, so Wigner, there's a lot of things in the theory named after Wigner, so that's yet another one. Wigner in 1931, so before quantum mechanics really got off the ground, very early, came up with Wigner Theorem, which says that physical symmetries are unitarily or anti-unitarily represented. Okay, so if you have some space-time symmetry, Poincare group, I don't know, then a physical theory should have some unitary action of it. So the proof is 2 steps. One is a physics step, namely to say, well, if there's a physical symmetry like a translation or rotation, that it should preserve something that is kind of strangely called a transition probability. It's not a very well-defined term, I think. I comment on this in a minute. Namely, it should be that the inner product absolute value squared of the transform states should just be the same as of the original ones. I comment on this in a second, whether or why that is reasonable. And so the step 2 is just mathy. So you take this relation, and then you work very long. It's kind of infamous for being a tedious and long proof, and in fact, Wigner's version was wrong, and Barkman proved it 20 years later. But the statement was correct, just the argument wasn't. That indeed anti-unitary or unitary transformations are the only solutions, at least in the absence of superselection rules. See, this doesn't sound like a quantum information talk, huh? All right, good. Let's talk a little bit about transition probabilities. This has nothing to do with my result. It's just that I'm an obnoxious person and I would like to lecture everybody about how they are wrong, and now you gotta sit through it. Okay, so because there is a bit, I think the justification for this is kind of subtly wrong in many textbooks. Now in physics, a wrong argument that happens to give you the right conclusion is allowed to live. In math, it's not the case. And so the reason, people say that this is true in physics textbooks is because they say, well, the empirical content of a quantum theory is given in terms of inner product absolute value squares, and so they must be preserved. And that's not quite right, because the physical expectation values are given by pairing a state and an eigenvector of an observable. But these are completely different objects, like in a generalized probabilistic theory, for example. So that they are both described by Hilbert space vectors in quantum is a super big coincidence. But it also means that under transformations, state vectors and eigenvectors of observables could transform completely differently. And so this is kind of obscured by using this prime notation, which hides the fact that a priori there are 2 different functions acting here. And so before you can even start doing the Wigner argument, you should, we have to clarify what this actually means, and it's not actually an inner product, it's not actually an expectation value. It's actually a measure of distinguishability between states. So these are 2 states, and the inner product absolute value squared between 2 states is also operationally well defined, because, for example, you can say that's the infimum over all tests that accept psi with certainty of the probability that this test can get confused into accepting phi. Right? And this is now physically well defined because here I'm pairing an observable and a state. And so pairing between states in this sense also has a physical meaning, and so Wigner was right all along and everything makes sense. Pooh! But that was a close call, no? So like Wigner theorem, the physics foundation is kind of wrong as usually presented, and the math proof was also wrong as presented by Wigner. So maybe we should think a little bit about the robustness of this result. And people have done it, and let me tell you about this story. Okay, Arno, first let me record this Wigner chapter, and then I tell you about how to approach this problem a bit differently. What happened next? Okay, so let's first make a definition. So a Wigner symmetry is a bijection of state space that preserves trace inner products. Yeah, I mean, if like now I wrote it on the Hilbert space level, but if you work in terms of projections, then it's the trace in the product. And the Hilbert space symmetry is a bijection of state space that's implemented by a unitary or anti-unitary on a Hilbert space. No, this talks about operators. This talks about state vectors. Okay, and so then what we have in quantum mechanics, which Bachmann proved and Wigner found, is that Wigner and Hilbert, they're actually equivalent. So Hilbert to Wigner is easy, but Wigner to Hilbert, that's the difficult part, but it's actually true. Okay. But then people in the 60s in the math phys literature, they looked at generalized notion of what kind of structure could be preserved in a quantum theory. Because these transition probabilities, they're a bit wonky, as I hope I made clear. And here's another notion that should be much better known than it is. It's called a Kadison symmetry. So a Kadison symmetry is a bijection of state space that commutes with convex combinations. Okay, so now we're not talking about state vectors anymore, we're talking about density matrices. And we are making a much weaker assumption than Wigner, right? Because we only use probabilistic but not metric properties, right? So a convex combination is just about the probabilistic structure of the theory. So it would make sense for GPTs in the sense of Martin, but and we don't use this. And also it's the type of symmetry of that we wanted to look at in the lambda polytope. So that's actually the right notion of symmetry for us. So, and given that this assumption is much weaker, it's a priori, there's an I missing, surprising that in the quantum case, not only do we have Wigner if and only Hilbert, we have Kadison if and only if Wigner, if and only if Hilbert. And I'll show you how to argue this in a second. All right. Oh, but since we are collecting symmetries, let's move on. And let's talk about Jordan symmetries. So then on the train very early in the morning, this morning, I was looking for illustrations and I have no idea how to illustrate a Jordan inner product. It's too algebraic. So I put into Google image search calm symmetric picture. And that's the first hit. It's calm and it's symmetric. So it's not the River Jordan or something. Okay. Good. And so you can have this inner product between observables that preserves hermiticity, and it's just the symmetrized version of the function composition. And now you can define a Jordan symmetry to be a bijection of Hermitian operators that commutes with Jordan products. Okay? And then it uses yet a different property of quantum mechanics, not the probabilistic property, not the metric property, but algebraic properties. And then what one can show is that in quantum, maybe surprisingly, we have the equivalence Kadison if and only if Wigner, if and only if Jordan, if and only if Hilbert. There's a lot, many dead men on these slides. But these are all now, I think, unless I die during my talk. Okay, doke. Wait, how did we get here? Let me move on. Now I can end my excursion into basic quantum mechanics 1, and I can state the actual problem I wanted to solve. So here's now the problem statement. It's I wanted to cite Reinhard. So Reinhard has this little thing on his webpage saying, describing his research style, and it ends with a word saying like that, phenomena in physics should be investigated, under the right sense of generality. So that's what defines himself. No? And so now I think we found the right level of generality for the symmetry of the lambda polytope problem, because it's not actually about the lambda polytope or the stabilizer polytope directly. We want to say the following. So we start with some subset Q that may or may not be quantum. I don't know. We call it Q because it's often round. So take that. And it's some subset of the Hermitian operators on a Hilbert space. And here are examples to which we want to apply our theory. So, for example, we could take all the pure states, or all the stabilizer states, or the set of mutually unbiased bases, or the seq POVMs, if you are old enough to remember what that is, or the real state vectors, or the real stabilizer states, or the phase-space point operators of discrete Wigner functions, different Wigner result, or the lambda polytope indeed. So there's many, operators like this, the symmetries of which people care about. All right, and then we want to ask what is the relation between the various symmetry groups. So Kadison Okay, Kadison commutes with convex combinations, Wigner preserves trace inner products, Jordan commutes with Jordan products, Hilbert anti-unitarily implemented. I added two more, namely two generalizations of Kadison, namely affine commutes with affine combinations and linear commutes with linear combinations. So these are two more. Okay, and we also look at the real versions where the Hilbert space has a real structure. And you ask about, and the set is contained in the symmetric matrices and not the Hermitian ones, what changes then? And so we want to understand when do we have equivalences between all these notions based on properties of Q. So what actually makes these results work? Okay. And that is my next slide. What are the relations between the symmetry groups? That's the question. Good. So now comes the actual part of the talk, the actual results here. Okay, so we have all these objects, Kadison, affine, linear, Jordan, Wigner, and Hilbert. And now there's a bunch of relations between them which are super trivial, and I don't want to talk long about them. So for example, if I have a Hilbert symmetry, it's implemented by conjugation, and therefore it preserves algebraic structure. So then every Hilbert symmetry is trivially a Jordan symmetry. But an action by conjugation is linear, so it's trivially linear, but every linear is affine, every affine is convex. So this is easy. Also, the objects I'm conjugating with are unitaries or anti-unitaries, so they preserve metric structure. So Hilbert implies Wigner. Okay, so that's what we start off with, in minute one. And the question is, what else can we do? All right, now I will, in the next 10 minutes, put many implications into this diagram. Okay, so then, so most of in fact, all of the implications we prove ourselves. There's one that we have outsourced to the literature, and that's the next one. It's the outsourced relation, and that is the implication from Jordan to Hilbert, meaning that the only way to preserve the Jordan algebraic structure of an algebra of matrices is by acting by conjugation. And this we outsource because this is the tedious part of Wigner Theorem. It's a lengthy but not very inspiring argument. And also it's well known. It holds in great generality about finite fields, in whatever you want. I think it's fair to say that's math and not physics. Okay? So now this allows us to compress the diagram a little bit because now Jordan and Hilbert are equivalent, so we can put it down. So we got Jordan, Hilbert. Okay? All right, so that was easy. Now we get something that, Arne proved in 3 lines, and then many years later we learned that it's called the Mazur-Ullmann theorem. All right. And that says that it's the following arrow. If you have a Wigner symmetry, it has to be linear. Yeah, so if you preserve trace inner products, then the only way to do this is by having a linear relation on, on operators. And it's very easy to prove. It's basically you define your symmetry on a generating set of points, and then basically you use linearity of the scalar product. And so linearity of the scalar product means that metric, if you want to preserve metric, you have to be linear. And apparently that's called the Mazur-Ullmann theorem. I didn't know that. All right, good. So now we are linear. Yeah, so it's much easier to draw. No, we have like a hierarchy, a clear linear ordering of these equivalences, and going to the left is easy. And now the question is, when can we go to the right? So that's when all the work starts. Okay, good. Now let's fill in the easy relations, because all these Kadison and affine and linear, they are very easily seen to be the same. So let me make that argument to you. Okay, so we have here's the space of Hermitian matrices, something. We have a set Q. It's not assumed to be anything like convex or bounded, or we have no regularity condition on it whatsoever. It's just 2 points. That's Q. And now the convex hull is here, the affine hull is there, and the linear hull is the blue area here, namely the entire space. And you can now see if I have a symmetry of Q, right, that commutes with the convex hull, I can just affinely extend it, and I can also linearly extend it, and vice versa. I can, if I have something linear, I can restrict it and it becomes affine. I can restrict it again, it becomes convex. So they are easily seen to be the same. There's only one thing that can possibly go wrong, namely if you go from between affine and linear, if 0, the point 0 is part of Q, yeah, then 0 is a distinguished point for linear maps, but not for affine maps, so we have to exclude that. So we can now clean up a little bit again. So we have Kadison if and only if affine, and if 0 is not in the affine hull, then also this is equivalent to linear. Okay? Right, so now we filled in all the easy arrows. Now come 2 arrows where we have to work. Well, I said hard, but it's not that hard. Yeah, but like the project was about what are the properties of a set Q, so that from linear you can go to Wigner, and from Wigner you can go to Jordan, meaning when is any isometry, sorry, when is any isomorphism of Q, when does it preserve metric information and when does it preserve algebraic information? So that's now the question. Okay? And that's where the appendix of this Heinrich paper came in, where in 2018 we had the idea of looking at moments of this object. Okay, so let me remind you what I mean by this. Well, what these are, and tell you what I mean by this and remind you what these are. Okay, so we have the set Q in the space of Hermitian operators, and we want to look at integrals over tensor powers. Okay, and so the question first is, what kind of integrals? And here I just take any Kadison symmetry invariant probability measure. That sounds very fancy, but in all the examples that we look at, there's actually a unique measure that has this property. For example, if you take all the pure states, it's Haar measure. If you take all these polytopes, it's a counting measure over the vertices. So in any case, I can now compute all these higher order polynomial pieces of information associated with the set. Okay, so let me make this a little bit more concrete. Okay, yeah, so for polytopes, which is of course the main body of interest here, these are, you may take, and usually it's unique, the normalized counting measure over vertices. So if you do it for the single qubit stabilizer polytope and q equal to 1, you just take the average of all these 6 points and you are smack in the middle and you get the maximally mixed state. Hold on to that thought because that is actually my entire next slide. Okay, because that's so trivial, I give it a Greek name and call it the barycenter. Well, that's what it's called, of course, in convex geometry. So the first order additional invariant that we have is, or like the first order information we get out here is the barycenter of the set. And because a symmetry, a Kadison symmetry, the weakest notion of symmetry we have, if it is an isomorphism of Q, then it must map the vertices to vertices. So it will just permute the vertices, and so it will just permute the terms in the sum here, so it will preserve the barycenter. Okay? And now as we argued for the qubit, and it's in fact true for all this like dozen examples I put in the beginning, the barycenter is always a maximally mixed state for all the examples we looked at. Right? So we have found a very trivial result, namely that all symmetries are unital. They preserve the identity operator. Or it will in a second turn out that it's better to think about the adjoints, and so they are trace preserving. Yeah, so we have trace preserving maps if we want to map such a quantum body onto itself. This is true for stabilizer states and quantum states in general. Very easy. Okay, so now that was extremely boring. Now to get more excitement, we have to go to higher orders, but now even getting a feeling for these higher order moments might not be so easy, so we look at one reference case and compare us to the reference case, and the reference case is all pure states, right? The scenario where we know that Wigner theorem and Kadison theorem and Jordan theorem, that they are all true. Okay. So the good thing is that there's a very easy formula for the kth moment of the set of all pure states, and by this gadget called Schur-Weil duality, if you take the average over something that is invariant under product unitaries, then this can be expressed as a sum over permutations. Okay, so SK is a permutation group on K letters, which will permute the different factors, tensor factors of the moment operator. Okay? Okay, now we know a definition, and it's a mild adaptation of a definition that has been around in the quantum information literature since like 20 years. So we say that a set Q behaves like a K design if it mimics the behavior of a Haar random distribution up to order K. Okay? So in particular, I can now say a very trivial thing with complicated language. All examples behave like one designs. Why? Because the barycenter is the identity, and by Schur's lemma, if k is 1, there's only the identity I'm summing over here. All right, so that was all extremely boring. So now let's look at second order moments, also known as the covariance matrix, associated with the invariant distribution over that body. Okay, so now here I'm summing over S2, which is the identity and the swap operator. So I need to get a feeling for this. And here I said before it's good to dualize and look at the adjoint. So here it turns out to be a good idea to not look at this tensor directly, but to take the trace inner product between this tensor and a product observable, A tensor B. Of course, you know, I'm just dualizing. There's exactly the same information in this bilinear function as there is in this kernel here. Okay, now I claim that if I plug in identity and swap, then I get trace A times trace B plus trace AB, and in fact in quantum information that's known as the swap test, this realization, and here's the graphical proof for why that is. You prove it using these wiring diagrams. So every tensor gets a little box, like A is a tensor, it has two indices sticking out to the left, B also, yeah, and then here let's look at the identity term first. Identity also factorizes, so I have two little boxes, and the trace means I have to contract these indices, which is in this graphical notation indicated by closing the loop. Okay, so now I have A and identity matrix composed. Identity goes away, the loop gives me the trace of A. So I got this term, trace of B, I got this term. Whoa! And now more exciting is the swap, where the tensor I'm contracting with is exchanging the indices, and if you follow the tracks here, you go from A into B and back into A, so that's trace AB. Okay, so now we've got that settled. Oh, but now we've already found the first result, because now assume that Q behaves like a 2 design, then if it's a K design, it's also a K prime design for all smaller K primes. So then these are the traces of operators. They are already preserved. That's what I said on my last slide. No, they're just saying that the barycenter is the identity. And so what is also preserved is this little gadget, which is nothing but the trace inner product between two Hermitian matrices. So there we are. So now we know that any distribution you can put into the space of Hermitian operators, if it has the same second moments as the pure states, will inherit the Wigner theorem right there. Yeah, like will mean any symmetry is like the Kadison-Wigner equivalence. Every Kadison symmetry, everything that respects the convex order, will also respect metric information. Okay, adjoint symmetries preserve inner product. So maybe this wasn't so surprising, because you know the fact that you have like a covariance matrix associated with a distribution, and that the covariance matrix is some kind of Euclidean metric. People have heard about this. So I think, you know, if we have any claim to, Kadison-Wigner, if we have any claim to like a novel structural insight, is that you can do it for third order 2, and there you get out algebraic information. Okay, so first we have added this arrow here, so we can go up here. There must be some salmon going upriver for spawning kind of Canadian joke here, but I'm not good at this, so I will not do this. All right, okay, so we are from the Pacific, we went up. I'm trying hard now. Yeah, and now we have to, like, you know, cross over one more barrier to go up to our spawning grounds. Okay, good. So third order. So now, all right, now we assume that Q behaves like a 3 design, and now we want to find out what does this little permutation formula give us here. And so, like, everything I told you was the storytelling. Now comes the only like structural insight that we ever had here. Okay, so now the moment is a sum over 6 permutations, because it's the permutations of 3 letters, so there are 6 of those, 3 times 2 times 1. And they are all reduced to things we already have. There's like, you know, the 1 cycle, they just give me trace A, B, C that I already know. And there are 2 3 cycles. And the 3 cycles, they look like this, no? So I have 3 operators A, B, C. Here is one, a cyclic shift downward. A maps to B, B to C, C wraps down up to A. And if I now compute trace A, B, C, mu har, then I get all these terms. Can you see it? All these terms that are just the old stuff that we already know is preserved. And then 2 3 cycles, trace ABC and trace ACB, which I get by closing these loops. And now we are almost done. So that's for you to be able to see it. So these are the new objects that are now preserved under 3 designs. And we are done, because So the adjoint symmetries preserve this thing too, but if I parenthesize it, that's just trace A, B times the Jordan product of C. So that means multiply in the Jordan sense B and C and expand into A. So that's also known as the matrix multiplication tensor of the Jordan algebra. So there we are. So any object that behaves like a 3 design must be so that its convex symmetries preserve the Jordan algebra. Okay. Aha, now we're done. So we put in, you know, the salmon went up the, how do we call it? I don't know, right? Okay, fine. So like on a 2 design property, we go to Wigner, and a 3 we go to Jordan. And so the main takeaway is that if anybody asks you about the symmetry properties of an object, you should compute its third order moments because that fixes algebraic properties of the symmetries. So that's the general result. And now back to the examples. So that were the examples I started with. And we can now put all the case here to which they are designs. They're all 2 designs. Some of them are 3 designs. Some of them are designs of any order. And now we can just, you know, work out.
You have time.
Oh, I have time?
To rush.
Oh, there's no need to rush. Oh, that's right. I have 2 timers here, and one was started when I tested the setup. So I have already rushed, so now I'm kind of done. So okay, fine. And I have one more message actually for you. Okay, so now we go back to the stabilizer polytope or the lambda polytope. But now you have a general method. You can do it for whichever set Q you want to. In any case, so if you have a single system n equal to 1, but arbitrary dimension d could be anything. In fact, it has to be prime or prime power. Then the set of stabilizer states is well known since the beginning of quantum information to decompose into a disjoint union of d plus 1 mutually unbiased bases. And so the symmetries, they were also known before, but we recover them, I guess, is you can permute the bases, but also independently within every basis, you can permute the states in any way, the element of the base in any way you want to. And so if you want to sound really smart, you say, oh, that's a Ries product. That's called a Ries product, but it's not spelled. No letter that I'm pronouncing actually occurs in the spelling of that word. So, you know, what's up with that English language? Okay, so now that's the n equal to 1 symmetry group. Then we have n larger 1 in dimension 2 or 3. Then conjugation with Clifford group elements are all the symmetries you get. And in fact, it's the extended Clifford group. Extended means you also have complex conjugation. So there is no new symmetries here, which is what we found in our Appendix B in 2018. Then if n is larger than 1 and d is larger than 3, then the symmetries are what is called, or we have called, I'm not super sure actually anymore, the affine symplectic similitudes. Okay, what does that mean? So affine means I'm having affine maps. These are all on discrete indices now, so on discrete state space, so I can shift things around in the discrete state space. I can also apply a linear part, S, and S is not quite affine because an affine map would preserve the symplectic inner product, but an affine similitude is a kind of like a conformal generalization. It maps the symplectic form to a multiple of the symplectic form. Yeah, and now we can differentiate. If alpha is 1, then it's symplectic, then it's unitarily implemented. If alpha is negative 1, it's anti-unitary, it's complex conjugation. And if alpha is something different, then it's also a symmetry of the stabilizer polytope and the lambda polytope, but it has no direct Hilbert space implementation. So that's a little bit, you know, that's a little bit bad that you have now symmetries that appear on the operator level, but you can't take the square root. You can't realize them by conjugating on the Hilbert space. However, you can, right? Because even though that is just, alpha is just like a number mod d, you can of course map it to an absolute value equal to 1 complex number, namely a d's root of unity. And then you can restrict from all the complex numbers to just the so-called cyclotomic field, which is the number field you get by taking the rationals and adjoining this d's root of unity. And then you take all the algebraic closures, you get something that's dense in all of C, but very different. And so this number field has more automorphisms than the complex numbers. The complex numbers just have complex conjugation as the algebraic automorphisms, but the cyclotomic field has more. And in if you restrict your quantum theory to cyclotomic numbers, then you can write down unitaries in cyclotomic, with cyclotomic entries, and they realize these similitudes. So it's actually still true that we kind of have some kind of meta Hilbert, I don't know, we could call it the Galois. One more dead man and one who died very young for pointless reasons. Oh, that's a missed opportunity. Now I have to forget I gave the talk so that I can give the talk again. I just have to remember to put Galois on the list of dead people. All right, okay, so in actuality, so all the symmetries, except for the n equal to 1 case, all the symmetries are implemented by some kind of conjugation, though if d is larger than 3, you have to be a little bit creative by what this conjugation, by the object you're conjugating with is. Okay, and then we can also do it for the real numbers, and yeah, this also works. Yeah, thank you.